For today, we're going to recap a little bit from what we talked about last week from the meta-learning problem setup and black box meta-learning. And then we're going to get into optimization-based meta-learning, where we're actually going to be embedding an optimization process inside another optimization process. And this is part of what we'll be talking about today is part of homework 2. And so it should also be useful for that. Great, and then yeah, by the end of the lecture, you should have a sense for kind of the basics of optimization-based meta-learning techniques and how to implement them in things like PyTorch, and also some of the trade-offs between black box meta-learning and optimization-based meta-learning. Cool, so to start to recap from last lecture, or some of the previous lectures, we've talked about multitask learning and transfer learning, and we introduced this notion of the meta-learning problem statement, which is kind of a form of transfer learning where our goal is, having been given a set of training tasks, we want to more quickly or more proficiently solve a new task. And we looked at this kind of running example meta-learning problem where we have, we're trying to do 5-way classification. We're given one example from each of the 5 different classes as this really tiny training data set. And our goal is to be able to predict the label for new examples as being among one of those 5 classes. And the way that we did this is we set up a set of tasks that look a lot like the kind of tasks that we'll see at meta test time. And so these were our training tasks, and we perform meta training on these tasks because we're trying to learn how to quickly learn each of these training tasks such that when we're given a new task at meta test time, we can quickly learn that task. And this was an example in image classification, but you can also replace this example with other machine learning problems. Great, and then one of the big topics of lecture on Wednesday last week was how we can actually solve these few-shot learning problems with a black box neural network, where we basically just pass in the training data set into something like a recurrent neural network, have that neural network possibly output a set of parameters for that task, and then we make predictions for new inputs for that task by passing that through the neural network with those parameters. We also talked about a second version of this where it's not explicitly outputting the parameters of an entire neural network. It's simply just giving you, for example, another hidden state of that RNN, and then you can just, again, pass that through the last module or the last time step of the RNN. So this kind of has this more general form where we're going to be passing in a training data set and a test input into some function, and we're going to be making a corresponding prediction. This method was great in that it's very expressive. You can represent lots of different learning algorithms with these large black box neural networks. But they can also be somewhat challenging to optimize, and that's maybe something that you came across in homework 1 if you've gotten started on that. So in this lecture, we're going to be thinking about other ways to try to represent this function that goes from a training data set to a set of task parameters. And in particular, we know something a little bit about machine learning. So you can think of this RNN as trying to mimic a learning process. And instead of trying to just throw a black box neural network at this, we could actually take a little bit about what we know about machine learning and actually apply that structure to this function and try to actually treat this function f as an optimization procedure. So that's what we'll really be focusing on today. So in particular, what we can do is we're basically going to replace this RNN on the top left with some form of optimization process. And in particular, we're going to focus on optimization, on gradient-based optimization. So instead of putting these examples into a RNN, we can instead we can actually run gradient descent on these examples in order to get a set of task-specific parameters. Now, the key idea here is that we're going to be embedding this gradient descent optimization inside a broader optimization process, the Metatraining process. And then the key question is, what are the meta parameters? What are we going to be kind of meta-training in this process? And there's a number of different free parameters of this process. What we'll focus on to start is a scenario where we are optimizing for the initial parameters of this neural network such that running gradient descent on a few examples gives us a good set of task-specific parameters for that task and for other tasks. Now, why might this make sense? So if we go back to a couple lectures ago, we were talking about fine-tuning. And we would take a set of pre-trained parameters, theta, and run gradient descent initialized with those pre-trained parameters. And we found that fine-tuning can actually work much better than learning from scratch. So we see that the green and orange lines are much lower. They have much lower error than the blue lines. But they also don't do great in the few-shot regime. And so essentially, you can think of this as trying to optimize for a set of pre-trained parameters such that we can actually do very well in the few-shot regime, unlike if we were just going to pre-train with something like supervised learning. So in particular, let's start to formulate what this looks like as an objective. So fine-tuning is what we want to be able to do at test time on our small training set for our new task. And so what we can do is we can take one step of gradient descent. We can also imagine more than one step, but we'll start with a simplifying case of one step of gradient descent. This will be used to get parameters for task I after fine-tuning on the data set for task I. And then once we have those parameters, we will evaluate how good those parameters are on new examples, specifically examples in the test data set for that task. And then we'll essentially optimize for the set of pre-trained parameters such that this one step of gradient descent is generalizing well to new examples. And of course, we won't just do this over one task. We'll do this over all of the tasks that we have available to us. And so this is essentially what our objective is going to look like for this optimization-based meta-learning process. So the key idea here is to try to learn a parameter vector, an initial parameter vector theta, that transfers very nicely with only a few examples. I mentioned that this is an example for just one gradient step, but in practice, you could also put multiple gradient steps in this inner loop here. And the equation will get a little bit longer, but this conceptual aspect of it is the same. OK, so from here we can, now that we have our objective, we can actually write out what this looks like as an algorithm. So again, we can think of the same three-way, one-shot classification problem that we considered in the last lecture, where basically different tasks will correspond to classifying digits from different alphabets. And in this case, you could sort of think of different alphabets as only having potentially 3 characters. And the first step, again, will be to sample a task. This will correspond to 3 different characters. Then the next step will be to sample a couple images per character. And this will allow us to basically give us a training data set and a test set for that task. And so in particular, we might have x equals a, b, and c, and y equals 0, 1, 2. And then also this will be our training data set, and then likewise a, b, c, and this will be the test set for this task, 0, 1, 2. And so before, what we did is we just passed the training data set through a neural network. Instead, what we're going to do is, I guess there'll be a step 0 here, which is to randomly initialize our metaparameters theta. And then what this step 3 is going to do is it's going to take one gradient descent step on our training data set. So we will start with our the current value of our metaparameters, then run gradient descent on our 3 training examples. And so I'll just write this as something like this. This will give us a set of parameters phi I. And then once we have these parameters, we will then take our test examples, run that through our neural network with parameters phi I to get a corresponding prediction. And so, for example, we'll be looking at f phi I of this example here. That will give us a corresponding prediction. And then we'll compare that prediction to the corresponding label to get how well this neural network is generalizing to new examples. And from there, we'll then backpropagate all the way back into the initial parameter vectors theta in order to update our metaparameters. And so, in particular, we'll have an update on theta, which will be based off of the how well phi I is doing on your held out examples d-test for task I. So this will be based off of ultimately the gradient of this. Cool. Now, one other thing that I'll mention here is, I guess I should maybe, well, actually, sorry. After step 4, then you'll go back to step 1 and repeat and continuously update theta based on this value right here. So this is the full meta-training algorithm. One thing that I'll mention here is, here we're going to be optimizing for some set of initial parameters, but you could also optimize for other parts of the inner loop learning process as well. For example, you could optimize for the learning rate here as well. And you could optimize with respect to some weights applied to the data points or something like that. Yeah, so this is the gist of it. Any questions on the meta-training process? Yeah?
I'm slightly confused about how like phi I and theta are related to each other. So at step 3, you get phi I from just modifying theta, but for step 4, you are updating theta using the gradient obtained through phi I. Okay. So that's the inner algorithm.
Yeah, exactly. So you can think of step 3 as the inner loop of this process because it's running the learning process on a task for task I. And then you can think of step 4 as this kind of outer loop objective where we're actually going to be differentiating through the inner loop process in order to figure out what would have been a better initialization that would have allowed me to better generalize with this small data set. The inner loop could also be more than one gradient step. It could also be a few gradient steps. Yeah.
This is similar to like online, offline methods like bootstrap your own latent, where you have like 2 separate networks that are kind of learning adjacently.
So the question is it similar to things like bootstrap your own latent and offline and online processes? I'm a little bit rusty on the details of BYOL. We will next week talk about unsupervised pre-training methods and talk a little bit about how those relate to meta-learning methods. Yeah.
Could you clarify again how this is different from like the black box learning algorithms from last week? Because, for example, if data in this case were the parameters of an RNN, then would we end up with something like pretty similar to what we had last week?
Yeah, so the key difference with the black box method, so this is black is the optimization-based approach. The key difference for the black box approach is really step 3. And so the difference with step 3 is instead of actually obtaining phi I through gradient descent, we obtained phi I by running it through a neural network. And so there was a neural network. I can't remember if I named it F or G in the previous lecture, but there's a neural network that took as input the training data points for the task and outputted the parameters. And now instead of just passing this through a neural network, we're going to be running gradient descent initialized at the metaparameters theta.
I
would this work when the loss functions between different tasks are different?
Will this work if the loss functions between tasks are different? Yeah, so you could certainly have different loss functions for different tasks. What you would do in that case is Li, you'd have basically have a, L would be kind of, you'd have a different loss function for different tasks, and so you would just need to use that loss function here and also here, and everything would all still work out. Yeah.
How do you make sure there isn't like some forgetting that's happening in beta? Like if you can imagine if you like loop over a bunch of different tasks and you come back to task one, how do you make sure, well, is there a guarantee that it'll still be as good as it was when you first started?
Yeah, so the question is, how do you make sure that forgetting doesn't happen? And as you loop through these tasks, it may not be as good at kind of the first task once after you've kind of gone through the other tasks. And really the key thing here is to, when you actually sample a task, you may also, instead of sampling just one task, you may want to sample a mini batch of tasks. And this will actually give you a gradient that isn't just, or a meta gradient that isn't just for one task, it's for multiple. You may ultimately get a little bit of forgetting insofar as like SGD will kind of forget some data points, for example. But having a mini batch, having a large enough batch size can certainly help with that. Yeah.
So the difference here is last time we were taking loss over the query set, but this time we'll be taking loss of the support set and train it in step 3. Am I right?
So the fourth step is still with respect to the query set. The
Test set?
Yeah, so the third step is really where the difference is, and so it is running a gradient step on the support set. Before we were also using the support set in the black box meta learning approach, and we were passing that into F theta, and so yeah, one key difference is here we're actually sort of taking a gradient step on both the support set and the query set. But the key step is the difference between 3. If you basically just put this into 3, then you get exactly the black box approach that we had last week. So one other thing that might help a little bit with some intuition here is that you can think of theta as this set of meta parameters that's being meta learned. And if you think about phi I star being the optimal parameter vector for task I, then you can think of meta-training as this really thick black line where when you're at this point in the meta-training process, if you take a gradient step with respect to task 3, you're quite far from the optimum for task 3. And likewise for other tasks. And as you kind of continue the meta-training process, ultimately at the end of the meta-training process, you want to be at a place in the landscape where if you take a gradient step with respect to task 3, you're very close to task 3. If you take a gradient step with respect to task 2, you're very close to a good parameter vector for task 2. So this may give you a little bit of a kind of a visual depiction of the meta-training process. Now, one thing I will note about this diagram that can potentially be a little bit misleading is there isn't just a single optimum for any given task. And so it's actually going to be more of actually a large part of the parameter space for any one task. And your goal is to try to find a part of the landscape where if you take a gradient step, you can get to a region that's good for that task parameter rather than just a single space. Yeah, that's the gist of it. In principle, this may, in this diagram, it kind of looks like it's almost averaging the task parameters. In practice, you may get something like that. In practice, you may also be in scenarios where you're actually pretty far from the average, but where kind of a gradient step will take you fairly far. And on that note, I think it's worth mentioning that this learning rate here, alpha, in practice will be much larger than a typical learning rate that you might use because you want to be able to actually go pretty far and actually be able to kind of traverse very far in the parameter space for different tasks. Yeah?
Like a hyperparametric tuning, right, with theta is the sorting value. If you frame it like Bayesian hyperparameter optimization, that like that improves the training of these optimization-based adaptations.
So certainly this does kind of look a lot like a hyperparameter optimization, except where you're optimizing the full initial parameters rather than just the learning rate. Your question was, can you also do hyperparameter optimization with this, or?
Like the expressivity base for that, like hyperop or something like that. Like if you frame this problem like that, it's like a dual optimization, but that works better.
Yeah, so you could certainly consider using hyperparameter optimization techniques for learning the initialization. Unfortunately, a lot of them are designed for optimizing a very low-dimensional set of hyperparameters, like 1 hyperparameter or 5 hyperparameters. And the initial parameters of a neural network may be millions of hyperparameters. And so a lot of those methods won't scale well to such high-dimensional things. And that's why in this case, we're actually going to just be differentiating through the learning process and using gradients. But there's a lot of ideas that are transferable between the two literatures. Yeah.
So here we are taking loss with respect to the DI train, right, in the third step. So what is loss here really? Because we concatenate the image and label, right, when we pass in, and then we are obviously trying to find the loss with respect to the training set labels again. That's outputted by the network.
Yeah, great question. So in black box meta learning, we were passing in both the image and the label into the network. Here, when we run this inner loop, we're going to have a model. We're going to have a model f theta that's kind of a neural network model, and we're going to be only passing as input the training examples into this. We're not going to be passing in the labels, and then we're going to get a corresponding prediction, and then this loss function right here, Li for theta di train, this is going to equal the sum over examples xi, yi in d train I of, I guess if it's something like regression, you'll have something like y hat train I minus y train I. If it's classification, you'll have something more like a cross entropy loss. And so this is kind of the definition of this loss function, and this is how you're going to get the gradient. And so you're not actually going to be passing in the labels into the network, but the labels will still come into play when you're comparing the predictions from the model to the ground truth predictions. Yeah.
How does optimization-based typically compare to block-based approaches, like performance-wise, and when would you choose one over the other?
Yeah, we'll talk about pros and cons of black box versus optimization-based towards the end. Yeah.
So as we're starting with the random parameters and doing this optimization, do we have to carefully design a learning rate schedule so that we have to lower the learning rate when we are at a good state of parameters, right? No.
Are you referring to this learning rate? Yeah, because there'll also be a learning rate here too. In general, yeah, it's a great question. So do we need to carefully schedule it? It is a hyperparameter, and you do need to pick it carefully. If you pick it to be too large, then it may be very difficult. Like the updates may be just way too large. If you pick something too small, it may have trouble actually differentiating and getting to different parameter vectors for different tasks. And so it's important to pick something that has a middle ground. The other thing that you can do is you can optimize it as part of step 4 as well. And what approaches have found is that it's actually helpful to optimize a different value of the learning rate for different layers or even for different parameters rather than having a single learning rate for all the parameters. And this is because some parameters, especially biases, like to have a very large learning rate and others like to have a very small learning rate. And if you try to optimize for a single learning rate for all of them, then they find a middle ground that isn't good for the weights. Yeah, so if you do optimize a different alpha for the different layers, it does actually end up being quite stable. Yeah.
For more generalization across tasks in step 3, can we add a term for regularization?
Can we add a term for regularization? So yeah, this loss function could also include a regularization term. One interesting thing here to note here is oftentimes you don't actually need a regularization on the inner loop. And this may be a little bit surprising because the inner loop data set is often really tiny. But because you're optimizing explicitly for generalization, it's going to be optimizing for at least a part of the optimization landscape that is nicely behaved and for which you don't get, you don't overfit. That said, it may be helpful to add regularization to this term here if you're worried about kind of overfitting to the tasks that you have. Yeah.
In this view, the training set is used in step 3, and the test set is used in step 4. And is it important to maintain that separation between the two steps, or can you commingle your images?
Yeah, so the question is it important to maintain this kind of distinction between train set and test set in step 3 and step 4? It is really important to have some held out data points in step 4 that are distinct from the data points that you're using for train. If you use the same exact data points, then you'll meta-train it to be able to memorize the things that you give as input and not actually learn the task that you care about. That said, when you do sample a task and when you sample the images in step 2, it's okay to kind of mix and match which images you use for train and test across these different iterations. The most important thing, though, is that within step 3 and step 4, that these are that you have some images in the test set that are held out. Yeah.
So my question is regarding testing return. Could we do any gradient descent there? Could we take any steps, training steps in the gradient testing?
You mean after the meta-training process?
Yeah, after the meta-training.
Yeah, exactly. Yeah, let's go through that. It's a great transition. So at meta test time, we are going to be given a task. You can call it task J, and then we'll also be given a training data set for that task. And after the meta testing process, what we'll be given is we'll kind of at the end, I guess the output is a set of meta parameters theta. And so what we're going to do is we're going to run gradient descent. So we're basically just going to run fine tuning starting from meta parameters theta on the training data that we have for our new task. So our estimate for the parameters for task J are going to correspond to theta minus alpha grad theta of the loss function for the training data set. It's a good idea to use roughly the same number of gradient steps in the inner loop in step 3 as you use at meta test time. You want meta training time and meta test time to match so that you are preparing the method for what will happen at meta test time. And of course, once you have these task-specific parameters for your test task, then you can make predictions on new data points by given an input, kind of pass it through your function f of phi j to get a corresponding prediction. Now, this algorithm, the algorithm where you kind of learn these set of initial parameters is referred to as model agnostic meta learning. And the reason why it's called that is that nowhere in here do you see anything about kind of a neural network architecture or model. And in that sense, the algorithm is somewhat agnostic to the particular architecture that you use. You can parameterize the model, the F model here, however you want. And as long as it's amenable to gradient descent, you can optimize for initialization of that model such that gradient descent gives you good generalization on the kinds of tasks that you meta train it on. Cool. So we've already gone through the algorithm on the board. Again, kind of the only difference from the black box approach is that instead of running the training data set through a neural network, we're going to run gradient descent on starting from our initial meta parameters. The other thing that I'll note here is, or just try to emphasize here, is like in the black box approach, when we evaluate phi I, we're not taking a gradient with respect to phi I, we're taking a gradient with respect to theta. And in this sense, we're sort of treating phi I more as activations than as weights. We're not ever running gradient descent on phi I itself. It's more of a kind of a product of the inner loop. Yeah, something to keep in mind. Yeah.
So on the same thing, why does it help to not train on fire?
The question is, why does it help to not train it on phi I? So phi I is kind of the output of step 3, and there's nothing that, if you then updated phi I in some way, there's nothing that then relies on that updated phi I in the process. And so it would sort of, similar to how when phi I was activations, it's something that sort of gets kind of wiped out at the next time you look at the task. Yeah.
Sorry, I might be ahead here, but do you have results to show? I see that you're the first on this paper.
Yeah, I can show some results.
I'm curious to know how this works better.
Yeah, so I was going to go through some math, but maybe I could skip to the results a little bit first and then go through some of the math. So this is kind of skipping ahead a little bit, but there's one paper that kind of actually ran kind of architecture search in addition to this algorithm, and so they were actually additionally optimizing for an architecture that is for which this actually works well. The kind of basic architecture on 5-way 5-shot mini ImageNet gets you 63.1%, which is a lot better than what you've been doing in homework 1, if you've gotten started with homework 1. And if you also optimize for the architecture, you can do even better than that. You can get up to 74%. The state of the art these days, I think, is in the low 80s at this point. And there's, we'll get into this a little bit later, but in general, these kinds of approaches are competitive with state of the art. Also, the approaches that we'll talk about on Wednesday are also competitive on these image classification problems. But I actually also think that the image classification benchmarks themselves are not the most interesting benchmarks, because even just learning good features can do very well on those benchmarks. And there are a lot of other application domains where getting good features isn't quite enough. And so we've seen applications in drug discovery as one example that can do quite well. I guess the short TLDR, though, is that these kinds of approaches can do quite well on meta-learning problems. Yeah. Yeah, I can't remember actually the specific approach that they used in this paper, but one thing that was interesting is that instead of, they found a fairly non-standard architecture, one that is actually quite deep and narrow, and typically deep and narrow things are not, typically you want enough width to be able to optimize, so it was kind of interesting that it found something a little bit different from that, but you can take a look at if you search for Kim and AutoMeta, you'll be able to find the paper. Cool. Let's go back to some math, though. So one thing that actually no one has brought up in the questions yet is that this is actually going to bring up some second-order derivatives. And the reason for that is that you have the inner loop here, which has a gradient with respect to theta, and you also have the outer loop, which also has a gradient with respect to theta. And so you might wonder, do we need to compute a Hessian? Hessians in deep learning are very scary because if you have an n-dimensional parameter vector, then the Hessian is going to be n squared. And so if you have a million parameters, that's going to be a million squared values in this Hessian. Also, if you want to run more intergradient steps, there's this question of, do you get even higher order derivatives? So we're going to do a bit of math. I guess to preface some of the math, if some of you are scared of math, PyTorch will do all the math for you. And so don't worry too much. But I think going through the math is actually really helpful for understanding what happens under the hood and what is actually the complexity of these algorithms in practice. So the first thing that you need to know before we get into the math of the meta-learning algorithms is about Hessian vector products. And the cool thing about Hessian vector products is that you can actually compute them much more cheaply than trying to compute the Hessian itself. And in particular, if we can actually compute these kind of metagradients without actually it'd be really nice if we didn't have to basically construct the whole Hessian in order to compute these metagradients. And so in particular, one intuition that you can think of for this is, say we have some function f. The gradient of that function is g. Then say that we are evaluating g of the gradient of f at x plus delta x. Then we know that this is roughly equal to g of x plus h of x times delta x. So this is just a kind of typical Taylor expansion. And from here, if we replace delta x by r times some vector v, so r is going to be some small value, g of x plus rv. So v is ultimately going to be the vector that we want to be able to compute. So our goal is going to be able to compute h of x times v. If you replace delta x with rv, then you get this equals g of x plus r h of x times v. And from this form, you can see that we can actually kind of move things around and actually solve for h of x times v. And what we get is h of x times v is roughly equal to g of x plus rv minus g of x divided by r. Can double check my math? Yeah. Yeah. And the cool thing about this is that it means that you could actually approximately compute this Hessian vector product with just 2 gradient evaluations. And that's really awesome because that means that we don't have to compute this giant Hessian. And this is going to be more expensive than 1 gradient evaluation, of course, but it's a lot cheaper than computing the whole Hessian. Now you might wonder, okay, we have this approximation sign here. Can we get the exact Hessian? And there are actually algorithms that have the same complexity that will also give you the exact Hessian. I'm not going to go into those, but Perlmutter's algorithm is one example of that. But this gives you a little bit of intuition for how we might go about computing these kinds of Hessian vector products. Cool. Yeah, so that's the good news, is if we can basically compute the metagradient as a Hessian vector product, then we can compute it with only around 2 gradient evaluations. Now let's go back to meta learning. So we and actually for notational purposes, we're going to have we're going to separately represent partial versus full derivatives. So I'm going to use ddx to refer to full derivatives, and the gradient of x evaluated x equals x prime, or x prime equals x. This will be kind of a partial derivative. That will help keep our notation straight a little bit. And remember that phi I is going to be equal to theta minus, let's use the full derivative here, d theta of L of theta comma di train. Cool, so this is everything that we had before. And our goal now is going to be to compute the gradient, or the metagradient in step 4. So the MAML objective is to minimize with respect to theta of the loss of phi I evaluated at the test data set for that task. So this is the same as what's written up there. And for this, we want to be able to compute the gradient of this with respect to theta. And so to do that, let's see, let's go over here. So we have d theta of this loss function. And now for this, we can use the chain rule. So if you remember your calculus, first we're going to take the gradient of the outer objective, and then we will differentiate from the inner. So we get the gradient of, I'm going to use phi bar here, of L phi bar of di test, evaluated at phi bar equals phi I. And then once we do the chain rule on the inner loop, then we just get d phi I d theta, because this isn't a function of theta right here. So this is the kind of derivative of our loss function with respect to theta. Here, this is a row vector. So we can refer to this as V. And this is a matrix. And then let's look a little bit more at this matrix right here. So this matrix, d phi I d theta, if we look at the definition of phi, we see d phi I d theta. Does anyone want to give it to me? What do I write next? Phi is a matrix.
Minus that.
Alpha. Yeah, and then the Hessian. Awesome, cool. I'm glad some people are paying attention. And this will be with respect to d train I. Cool. And so if we plug this expression in to here, what we're going to get is this is equal to v times I minus alpha v, times h right here. So this is just the Hessian right here. And that's great because we then get a Hessian vector product right here rather than anything that has to do with the full Hessian. Can people see this? Is this too low? It's okay, okay, good. Cool, so to answer the first question, we do get second order derivatives here, but we only get this Hessian vector product, and so in practice, to compute the metagradient for this algorithm, it just requires a few extra backward passes of your neural network. It doesn't require anything more than that. Yeah?
Like with like multiple integrating steps, then does this change at all, or?
Yeah. So then the question is, what happens if you do multiple gradient steps? So if you do multiple gradient steps, then your phi I is going to be equal to theta minus alpha d theta L of theta di train. This is just the first step. And then the second step, you're going to be running a second gradient step on this parameter vector. So if we refer to this parameter vector as theta prime, then this next step is d theta prime of L theta prime di train. And the key thing to note here is this second gradient step is with respect to theta prime and not with respect to, well, it's with respect to theta prime first, and then second, this isn't like, when you take a second gradient step, it's not like a second order gradient step, it's just a second gradient step in sequence. And so when you actually go to compute the metagradient, you get the same exact form as before, except now we have a different d phi I d theta. And so what we're going to get for the new d phi I d theta is going to be the same as before, but now we're going to have a third term, which will look like minus alpha times this differentiated, we need to differentiate this third term by theta. And what we get there is something like we do the chain rule again, so we're going to do theta bar prime L theta bar prime di train. This is going to be evaluated at theta bar prime equals theta prime times d theta prime d theta. And so basically you'll get kind of these products of Hessians, but you don't get anything that has a 3 on it. And that's good because the higher this number is, the nastier it gets. Yeah.
So this tells me that the 3 and 4 are coupled gradient steps. So you take one gradient step in 3, and then you do 4, and then you go back and do 3 and do 4 for an entire mini batch, let's say.
Right, so if you were to take multiple gradient steps, that just means that the equation on step 3 will be different. Instead of taking one gradient step, you will have 2 gradient steps, like what's written here. And so the only thing that, if you take multiple inner gradient steps, that's changing is just that the equation in 3 will be a little bit different.
How do I know theta prime at 4th step when I've already completed the multiple gradient steps at the 3rd one?
When you actually backprop through, you need to actually store all the intermediate parameter vector values. Because basically you can think of it as the forward process of this inner loop is running gradient descent, and then to backprop through that again, you need to kind of backprop through those gradient steps. And so while we don't get 3rd order gradients, if you have a lot of inner loop steps, it will increase the amount of memory usage linearly, and also increase compute as well. Yeah.
Is taking multiple gradient steps worth the overhead?
Yeah, so the question is taking multiple gradient steps worth the overhead? For few-shot learning problems, you actually don't need a very large number of gradient steps. You can actually do quite well with a pretty small number of gradient steps, between like 1 and 5 gradient steps. And so in practice, at least from what I've seen, you don't actually need like more than 5 inner gradient steps, and that ends up working pretty well on few-shot learning problems. And it's also not that expensive. If you wanted to run 100 gradient steps, things get a lot more expensive. And in 2 weeks, we're going to talk about more advanced meta learning techniques, including ways to differentiate through like hundreds of gradient steps. And doing something like this with hundreds of inner gradient steps is not a great approach. Yeah.
Yeah, so I'm just trying to connect these like Hessian vector parts with the final formula that we have. So is R the same as alpha in this case? Like the
R here. So you can think of this as a finite difference method, and R just needs to be small here. And so it's not quite the same as alpha. The biggest thing is that V is the same. So V here is the same as V there. And R will be separately chosen. So alpha is just going to be the multiplier based off of the inner learning rate. Whereas to compute this, if you wanted to use finite differences to compute this, you would separately select a small r to use with finite differences. And in practice, things like PyTorch will not use finite differences. They'll actually give you an exact Hessian vector product. Yeah.
It's a train, right? Like it's just a bunch of samples and they're not labeled.
So dtrain does have labels. So it will have both the examples and the labels. You'll only be passing the examples into your neural network. But then to compute the gradient in your inner loop, you'll use the labels there.
In the black box version, we did not need the labels, right? Because we just need to find like which class is the most similar to one of like the sample we have in dataset for the test.
So in black box meta learning, we also actually did need the labels as well. And so we were actually passing those in to the neural network as well. And the reason why it needed that is it needed to know what to output for this letter. And so it could tell you, okay, it's the same class as this, but then it needs to give you a number for that class. And so we passed in the labels for that reason for black box as well. It's supervised, yeah. Yeah.
Black box method, we would change the labels for the A character, everyone then deciding a 0 level, something or 1 level is does it still apply here?
Yeah, it does still apply. So the question is here the label, we assign label 0 to A in this task, but in another task you might assign a different label to A because the assignment of labels to images is somewhat arbitrary in classification problems. And so it's also useful to kind of randomize that assignment across tasks.
Problems, and for other problems we just keep the label intact.
Yeah, so for things like regression problems, you'll typically keep the label intact, yeah. And we'll talk a little bit more about some of that stuff in 2 weeks in some of the advanced meta learning topics. So.
PyTorch does the Hessian first, the Hessian.
The Hessian vector product, yeah.
And that's by default, that's for PyTorch.
Yeah. So here's my slide on that. Any other questions? Oh, question? Okay, cool, good. Okay, we also went through meta test time already, but it's on the slide in case you want a reference for that. And the gist of it is just to run fine tuning. Cool, so yeah, that was really the kind of overall basics of optimization-based meta learning. Now let's compare optimization-based versus black box meta learning, and then also talk about some challenges and solutions. If we have a little bit of time, we'll also look at a case study at the end. So at a conceptual level, there's a way that you can look at these two things in a way that's quite similar. So the general form of black box adaptation was to pass in the training data set and the test input into this big neural network and get a corresponding label or corresponding prediction. For an algorithm like MAML, you can also view it in a very similar light as a kind of a computation graph that takes as input the training data set and a test input. And the way that it looks like that is essentially you can view it as a computation graph that just has a gradient step inside the computation graph. So dtrain and xtest are still inputs to that overarching computation graph. It's just that it has a gradient step inside of it where we're taking a gradient with respect to our training data points to get our parameters and make predictions based on those parameters. So from this view, they end up looking more similar than perhaps they look like on the previous slides. And also from this view, it means that you can somewhat mix and match components of your computation graph. And there are methods that, for example, have like learned an initialization, but replace the gradient update with a learned network. For example, this paper does something like that, where it learns data, and it also learns this network that kind of takes the gradient and warps it in some way to predict a different gradient than the actual gradient. And this paper actually precedes the MAML paper. And I guess I mentioned this as a kind of a conceptual thing that's kind of interesting. In practice, I wouldn't recommend using this algorithm. It's a little bit more complicated and tends to not work as well as actually just using the gradient. But it's something that I think is useful to know conceptually. Cool, and then we'll also look at this again on Wednesday when we look at a third class of approaches. Now let's actually look at how these algorithms perform in practice. So in general, both of them can represent a variety of learning algorithms. But one thing that's nice about the optimization-based meta learning algorithms is that at meta test time, you're like literally just running fine tuning. And so even if you don't actually have a very good set of meta parameters, fine tuning should still give you something that improves on the parameter vector that you have. Whereas if you just throw something into a recurrent neural network, you can't really expect it to necessarily give you something reasonable if the data set is out of distribution from the task that it saw before. And so we can explicitly test this. And so we're going to compare an optimization-based algorithm, MAML, with two black box algorithms called snail and meta networks. And specifically, we're going to look at omniglot image classification, and we're going to look at performance as you vary the task. And in particular, the first thing we're going to look at is all of the algorithms were just meta-trained on the original omniglot data set, but then we evaluated them on tasks that had digits that were warped. And so they were all trained on kind of the center line, so they're going to do the best at the center, but then as you warp the characters more and more, the performance will get worse because it's more out of distribution. And so what we find here is that an algorithm like MAML actually is able to generalize much better to these out of distribution tasks compared to something like the black box metalearners, because it has this kind of structure of running gradient descent embedded within it, and it's just running fine-tuning at test time. We can also look at this on a second task. This is where kind of warping the size of the digits. And here we see a similar trend where the optimization-based algorithm is better able to extrapolate. Yeah.
As a baseline, can we treat like the parameters that come from the black box model and fine-tune them on the training set, like the Metatraining set for the test task, and just check the performance?
You're asking, can you, as a baseline, can you fine-tune the black box meta learning?
Yeah, black box parameters that are being predicted, and then fine-tune them a bit on the training set.
Yeah. So if you have a black box meta learner that's actually outputting parameters, then you could also fine-tune those parameters a little bit, and you would expect that to do a little bit better than if you didn't fine-tune. Both of these approaches, Snail and meta networks, are not actually outputting a single set of parameters, but you could sort of like fine-tune the last part of the RNN. And in principle, that should improve it a little bit. I suspect that it may not improve it all the way up to the purple line, but I suspect it would improve it a little bit. Yeah.
What could explain this rapid fall in accuracy, which comes in the scale and not so much in the shear?
Yeah, so the question is, why is it dropping more rapidly for the scale versus the shift? I should say that the x-axes on these two plots are not very comparable. One is in like scale, and one of those is in radians. And so if, for example, you zoomed out more on the radians plot to show a wider range, I would expect it to drop off more quickly. I also think that as you make a digit smaller and smaller, it's probably a little bit harder for the neural network to read than the larger one. And so that's, I expect, why we see more of a drop off on the left side than on the right side, but that's somewhat speculative. Yeah.
So what is the underlying model architecture chosen for both algorithms, for all the?
What is the underlying model architecture? So for MAML, it's a 4-layer convolutional network with, I think, like 32 filters, something like that per layer. And it's kind of a standard architecture that's been used in multiple works. Whereas for Snail and meta networks, the architecture is a little bit more specific to the method because it's a kind of a non-model agnostic method. It's kind of, yeah, and so Snail was the one that used the interleaved convolutions and attention layers.
That helps convolutions and attention layers as well to for the scale and the shifting part.
You're asking me if the convolution layers help?
Help with understanding the variance in the data distribution, which is the scale and the shift, whereas the Snail, I guess, just use RNNs, right?
So Snail was using, I can't remember if there was, I'm pretty sure there was a backbone that was convolution based. And likewise for meta networks. I can't remember the specifics of it, unfortunately, but I'm pretty sure it is using that. And I should mention and emphasize here that all of these were only trained on this scale. And so they didn't see any data at different scales and different shears of the digit. Cool. So we see that the structure of gradient descent is helping us generalize to out of distribution tasks. Now you might wonder if this structure comes at a cost because maybe, for example, by embedding gradient descent, we don't have as much expressive power in terms of the algorithms, the learning procedures that we can represent. And it turns out that you can actually theoretically show that if you have a deep neural network, the kind of MAML function of running one step of gradient descent can actually approximate any function of the training data set and the test input. So it can sort of approximate any learning algorithm. Although it does make some non-trivial assumptions. Well, it assumes that the learning rate is non-zero, that the data points are unique, and that the loss function gradient does not lose information about the label. But really the strongest assumption is that the network needs to be extremely deep for this sort of result to hold. And you can get more expressive power with the RNN-like approaches with a smaller neural network. Yeah.
What does it mean for a loss function gradient to lose information about the label? Or either way, but...
Yeah, so essentially what that means just very approximately is if you have one loss function that that looks like this versus a loss function that looks like this, if you just look at the gradient of this function, you don't actually know where you are on the line at all. And so that doesn't tell you, you know what your prediction is, but it doesn't tell you what the label is relative to your prediction. And so it doesn't hold for L1 loss functions, but it does hold for things like L2 and cross-entropy loss. Yeah?
Why is it that the data points in the data set needs to be unique?
Yeah, this is a little bit getting into details that aren't super important, but the gist is that if you have duplicates of data points and you want it to give you different phi i's for different numbers of duplicates in the data set, it's hard to understand how many duplicates there are in the gradient. For example, if you think about the gradient of 2 data points versus the gradient of 5 data points that are identical, the gradient is the same because it's just averaging across them. And so it's not going to, the learning algorithm isn't going to be able to differentiate between, it's not going to be able to count the number of data points you have, basically. Yeah.
Each technique, or is there any point in using black box optimization?
Yeah, let's go through some of the challenges and solutions, and then, well, I'll get into full depth of that on Wednesday, but I'll also talk more about the pros and cons after we go through some of the challenges and solutions. So one reason to not use these kinds of optimization-based methods is that sometimes this sort of bi-level optimization can be somewhat unstable because you have an optimization inside another optimization. And there are ways to try to stabilize the process. One way to stabilize it is actually to give it a little bit more expressive power. Don't just learn the initialization, but also learn the learning rate. And this has been shown to, at least in practice, lead to an easier outer optimization. There's also approaches that try to only optimize a subset of the parameters in the inner loop. For example, you could choose to only optimize the last layer in the inner loop, or choose to only optimize like the batch norm parameters in your inner loop, or something like that. And then there's also some work that showed that if you have a different learning rate and a different batch norm statistics per gradient step in the inner loop, that can also help stabilize things, because if they're coupled, then they, whenever you have basically the same value for something, it can cause those values to sort of fight during the optimization process and not find a good, happy medium. And then, I don't want to go into too much depth in this, but there's also approaches that try to kind of introduce a sort of context variable that instead of only optimizing for the parameters of this neural network, you can essentially add a variable that's kind of part of theta here as part of the network. You can sort of think of this as kind of like the zi that we saw in multitask learning, that you're optimizing as well as the other parameters. And this can also kind of increase the expressive power of the meta optimizer, and in practice leads to better results as well. I'm more giving this just as an overview if you want to dive a little bit deeper into things that can help these algorithms work better in practice. Cool, so yeah, range of simple tricks that can help the optimization a lot. And then the second main challenge I want to talk about is that if you have one or a few inner gradient steps, it's very easy to differentiate through that. But if you have a lot of inner gradient steps, it becomes very compute intensive and very memory intensive. And there are also a few tricks for trying to address this. The first trick is a bit of a hack, and it's actually something that I discovered because of a bug in TensorFlow. And in particular, the first time that I implemented the MAML algorithm, it turned out that TensorFlow didn't properly implement this, this term, and it just silently basically set this to be the identity. And it turns out that actually if you set it to be the identity, it actually works some of the time. And so for simple image classification tasks, you can actually, and that's not the identity, by the way. And so, yeah, it turns out to actually work in some cases. There's another paper that explicitly proposed this sort of first order method as well. And so if you do approximate as the identity, you don't have any second order terms. And it can work well on simple problems. In other problems, I've found that it doesn't work well at all.
Is that why we're using PyTorch and not?
Not quite. I mean, TensorFlow has since fixed this issue. This was very early days in early 2017. Yeah, but since then both, and actually the early days of PyTorch, they also didn't have their second order derivatives properly implemented as well. So, yeah.
You make that assumption, do you essentially assume that phi I is very similar to theta?
So it's basically saying that the loss landscape around phi is very similar to the loss landscape around theta. I don't think we know why it works. Although my guess would be something that it has to do with the optimization landscape being well conditioned. But yeah, we don't fully know why this works. Yeah.
So if that was set as identity, does that mean that the Hessian was not getting calculated correctly, it became a 0, therefore I, or?
Yeah, so this was being set to 0. Yeah.
So it did not know how to calculate it.
I don't remember the exact details of the bug, but it was something like, I think it was something like basically the Hessian wasn't implemented or something, and it was silently returning 0 rather than throwing an error.
But why does identity work then?
We don't know.
It's an observation.
It's an observation, yeah. Another thing that you can do is if you don't want to backpropagate through many integrating steps of the whole network, if you only optimize the last layer of weights, then this can actually be very cheap. There are a number of papers that have done this that actually get quite strong results. And in some of these cases, you can actually compute potentially the last layer in closed form. And that has a number of benefits. This works especially well in settings where, in like image settings where learning features are a big part of the problem. Cool, and then there's also something called the implicit value theorem that is actually pretty cool. It allows you to differentiate the metagradient without actually differentiating through the optimization path. We might talk about this a little bit in some of the advanced meta learning lectures, but I more mention it here as a reference in case you're interested in digging deeper into that. Yeah.
And the second idea, is it only optimizing the last layer in the inner loop or in the outer loop?
In the inner loop. So in basically, yeah, in step 3, you only optimize the inner loop, and then step 4, you optimize the whole network such that, basically optimize for features such that optimizing the inner loop gives you a good performance. Yeah.
Layer works the best, like the paper you mentioned.
Yeah, so you could also think about fine-tuning different parts of the network. You could also have something where you fine-tune the last layer for some tasks and fine-tune the first layer for other tasks. Although then there's this, you have to actually select which layer to adapt for different tasks. There's also a paper that actually optimizes everything but the last layer, and they actually found pretty good results with that. I'm not exactly sure how they came up with it. It's called Boil, if you want to look it up. But yeah, you could imagine something like that. Cool, and then I already showed this slide, but there's also some works that have looked at architectures for this kind of bi-level optimization and have found that actually sometimes deeper and narrow architectures can work pretty well. And yeah, that's the gist of it. So the takeaway here is that we're constructing this bi-level optimization problem. In terms of the pros and cons, one thing that's really nice about it is it has this sort of positive inductive bias at the start of meta-learning. And what I mean by that is before you do any meta-learning, you're already running gradient descent on your training data set in the inner loop. And that means that you already have a pretty good starting point for learning from data. And in contrast to black box approaches are starting with a randomly initialized recurrent neural network. And so when you pass in a data set into that randomly initialized neural network, it doesn't have any sort of inductive bias at the beginning that will give you, that will actually do anything remotely like learning at the start of initialization. Because of this, it tends to extrapolate a little bit better because you're embedding gradient descent, because you're running fine tuning. And it's also quite expressive if you have a deep enough neural network. And it's model agnostic. The downside is that it does typically require a second order optimization, which can be computationally, it's certainly a little bit more expensive than other approaches, especially the approaches we'll talk about on Wednesday. And so this leads to more compute and memory usage. Cool. We have 6 minutes, so I think I will go through this case study. We'll also look at some more case studies on Wednesday this week. So this was actually some work done by some folks at TUM and also some folks at Stanford. Sherry was actually a PhD student at Stanford. She graduated, I think, last year and is now starting as a professor at MIT. And this is some work that they did on trying to do land cover classification. And the motivation is that if you have a satellite image, it's useful to be able to predict how the land is being used. This can be used for urban planning, for understanding how things are changing over time. But it's very expensive to label these satellite images, as you might imagine. And so labeling data is really expensive. And different regions look different and have different land use proportions. And so this means that if you train a model on one part of the world and then try to apply that model to other parts of the world, it may not generalize well to all parts of the world. And so what they were looking at is they had croplands from multiple different countries, and they framed this as a meta-learning problem where different tasks correspond to different regions of the world. And so what they wanted to be able to do is, for a new region of the world that they didn't have labels for yet, they wanted to label a small amount of data for that region, and then get a good segmenter or classifier for that region of the world that can basically fill in the rest of the labels. And so you can sort of think of this as, this is a diagram from their paper where you try to find a good set of initial parameters such that when you fine tune on a new region of the world, you're able to quickly get a model that can accurately segment satellite images from that part of the world. So they looked at 2 different data sets. One of the data sets had geographic metadata in it, and so they were able to separate out kind of explicitly separate out new regions of the world. And so dark blue is meta-train, light blue is meta-validation tasks, and orange is meta-test tasks. And kind of as an example of a 2-way, 2-shot classification task, they're trying to classify if a square is forest or croplands. And so they're given that, and then they have 2 examples per class of what those parts of the land look like. And then they also had a second data set where they were looking at, where they didn't have any kind of geographic metadata, and so they used clustering to try to guess the region of the world and separate things out into meta-training, meta-validation, and meta-test. And here they were doing a kind of a segmentation task where they were basically, the support set corresponded to one small square, and then the query set corresponded to the other squares. Cool. And so they were comparing random initialization, so they're training from scratch on a small amount of data from that new region. They also compared that to pre-training on all of the data they had so far and then fine-tuning on the target task. And lastly, they compared to the MAML algorithm that we talked about today. And what we see is here is the results on the first data set. And this is the performance or the accuracy of land cover classification as you increase the number of data points on the target task. First, we see that random initialization isn't able to do very well because it doesn't use any other data. Using a pre-trained network is able to do a lot better, especially with less data. And then MAML is able to do, if you have one or more data points from the target region, is able to do even better than a pre-trained neural network. One benefit to the pre-trained neural network is it can actually already do decent classification just without any additional data from the new region. And so that's why the dark blue is above the orange and the light green at 0. And then likewise on the deep globe data set, they looked at both a random split and a harder clustered split. Here, the results are similar on the clustered split. On the random split, they actually found that the pre-trained model was able to do quite well, which makes sense because the kind of the pre-training data and the target data, you're going to basically have more data points that look more similar across the kind of pre-trained data and the target data. Cool, and then if you're interested in looking at this more, I'd encourage you to take a look at the paper. Here's just kind of, just one example of a fairly real world problem of using this kind of approach. Cool, so that's it for today. We covered the basics of optimization-based meta-learning. We talked about how it compared with black box meta-learning. On Wednesday, we're gonna be talking about our last type of meta-learning method, non-parametric few-shot learning methods. Then next week, we'll talk about unsupervised pre-training. And the following week, we'll talk about more advanced meta-learning topics. And as a reminder, submit your project form and your homework on Wednesday.